Thank you all for attending this next one in the Applied PD seminar series. It's a great honor to introduce Professor Walter Strauss from Brown University. Walter is the L. Herbert Ballou University Professor at Brown. He is a professor both in the mathematics and in the applied mathematics department. He is the author of two very well-known books and hundreds of papers. He was actually he is a fellow of both SciAm and AMS. He was actually part of the inaugural class for both of these. He has many contributions on nonlinear wave equations, including the water wave problem, which we'll hear about today, plasma physics and astrophysics. His contributions are many. He's worked a lot on stability, which is also the topic of today's talk, but also on scattering, kinetic theory, bifurcation theory, which I think is also included in today's talk. And I'm sure we're in for an excellent talk today. Thank you, Walter.
Well, thank you, Bernard, for a nice introduction. It's really a pleasure to come to Seattle. I wish it was in reality rather than virtual. Yeah, so what I'm talking about is proof of the modulational instability of Stokes waves, which I'll explain in a moment. And everything I'm talking about in today's lecture is joint work with Huy Q, Nguyen, who is at the moment a postdoc at Brown. Okay. Oops. Let's see. All right. Yeah. All right. Here's the outline. Well, from basically, except for A and B, it's basically the proof of this instability. But we have to set things up. The most important things in the proof are the linearization, and then later on the Lyapunov-Schmidt decomposition. Okay, so let me begin by just saying what the basic setup is. So first we start with a Stokes wave. By Stokes wave, I mean a periodic traveling water wave propagating in some direction. And I'm going to be talking about, in this lecture, I'll talk about 2D traveling waves. So it's just traveling horizontally. And there are many kinds of instabilities that are very famous in hydrodynamics, such as the Rayleigh-Taylor, Kelvin-Helmholtz, and various others. But I'm talking today about the modulational, or often called the Benjamin and Feir instability. So if one takes one of these Stokes waves, let's say a small Stokes wave, and you perturb by a slightly different wave number, then the wave will deviate from the original Stokes wave in time and grow exponentially, at least for a certain, grow exponentially. So that's what, basically in a few words, that's what I'm talking about. So I'll write down the Euler equations in a moment. You have the Euler equations, which say what happens in a fluid. Maybe I should draw the picture first. Here's a simple picture drawn freehand, where you have, I'm going to be talking about 2D waves, so the other horizontal coordinate that's independent of that. So I'll use y as the vertical, and the surface is given by a function y equals eta of x and t. And if it's periodic, then it has some period L, which I'll take to be 2 pi for simplicity. And your gravity pointing down and a flat bottom. Okay, let me go back to what I had before. Okay, so the assumptions in words are you take the Euler equations, and so that means the water is inviscid. And I will assume it's irrotational and incompressible. And the surface conditions are the simplest standard ones. The pressure on the surface equals the air pressure, which is a constant, and the particles on the surface remain on the surface. That's the two free surface boundary conditions. It's very standard. So here's the picture. And now here I write down a little notation. So remember, I'm just assuming we're in 2 dimensions, x and y is vertical. So here's the domain, and I'm going to be concentrating, even though I don't have to, I'll concentrate on infinite depth. Okay, and the surface is y equal eta. And so here are the equations, which it's not the original form of the Euler equations, but for irrotational incompressible flow, we can write down, the velocity vector, a two-dimensional vector, is the gradient of some function, the velocity potential. And the velocity potential is harmonic. That's Euler's equation. And the boundary, that's Euler's equation. So in the domain, omega is the fluid domain. So in the domain, you have 2 boundary conditions on top. This one is sometimes called Bernoulli's equation. P is atmospheric pressure, and this is the statement equivalent to the statement that the pressure on the surface is a constant. And this boundary condition is just saying that particles on the surface remain on the surface. And this boundary condition is at infinite depth. I'm doing the infinite depth case. So in that case, the velocity goes to 0 as you go very deep. That's this state. So that's exactly the whole problem written here, the basic setup. Okay. And a Stokes wave is a solution of that system, which is traveling. So it depends only on x minus ct and y. C is a constant, the speed of propagation, and time then basically disappears from the problem. And of course, this was studied, especially by Stokes in the mid-19th century. And then a rigorous proof of the existence of these exact traveling waves was done by Nekrasov and Lebechivica in famous papers around 1920. And are they stable? Well, there was actually, well, in 1967, Benjamin and Feir wrote this important paper, and it was also influenced by Lighthill and Whittam. There was a group of people in the late 60s who showed analytically, but not rigorously, that rather heuristically, that you have this instability that I mentioned before. So that means you take slightly different wave numbers, which they call sidebands. Benjamin called them sidebands. Okay. Now this instability, there are hundreds of papers talking about modulational instability. And some of them are really in the physics or engineering literature there, many of them, probably most of them. But there was no proof for almost 30 years until Bridges and Mielke wrote a beautiful paper where they gave a rigorous proof of the linearized instability by spatial dynamics method. But that proof does not work for infinite depth. And so Huy, Nguyen, and I have a new proof that works for infinite depth, but also works for finite depth. And it's really very different from the Bridges-Mielke. We don't use a spatial dynamics point of view. An alternative proof has recently been announced after we did ours by Vera Her. Okay, so I should mention that there are many, many approximate models, as I'm sure almost all of you know, like KDV, NLS, Whittam equation, and many other approximate models for water waves. And the modulational instability, linearized, has been studied specifically in the 2000s by all these people, Bronsky, et cetera. And there's a paper on the nonlinear instability for some of these models by Jin, Liao, and Lin recently. But what's distinct about what I'm talking about here is the full water wave problem, not an approximate model. So I just want to emphasize how this differs from other papers. So this means Bridges and Mielke. Bridges and Mielke, it won't work in infinite depth because that introduces continuous spectrum into their point of view. And so they can't use the center manifold theory. But as I say, our proof works for any depth. And the proof is actually very different. And our proof uses more or less standard energy estimates as its basis. So as I said, this talk focuses on the linear instability with case of infinite depth. The finite depth is a lot more algebra to do calculations, but it's the same idea. So here's here I'm going to state precisely the result. You take a Stokes wave, say of period 2 pi, and there's a family of Stokes wave parameterized by a number I'll call epsilon. I'm only going to be talking about small Stokes wave. So it just deviates slightly from a laminar flow. And then we perturb the wave number. I'll write it more carefully later on. And that means that you take your various periodic functions, you multiply by e to the I mu x, where mu is small. Mu is small. So epsilon is small and mu is small. And then we linearize, which I will define very carefully later. That's going to be the focus of what we talked about. We're going to linearize. We get a linearized operator depending on these two parameters. And then the linear operator has, the statement is the linear operator has an eigenvalue with positive real part, which is the instability. And here is the positive real part right here. It's 1 over the square root of 8 times mu epsilon. This one is imaginary. Here's the real part, and these guys are error terms. So I'll be more precise about some of these things, but this is the theorem. Okay. And so there's a very nice numerical paper of Bernard and Oliveros, Katie Oliveros, where they compute a lot of things of this type. And here's one of their pictures. And the result I just showed is consistent with this picture. You notice the scale here. This is a very small scale, very fine scale here. So, and this is a wide scale. So it's really a very flat, this figure 8 is very, very flat if we had the same scale. Okay, so now for the proof, for our proof, we start with the Stokes wave, we linearize, and we transform to a fixed domain without a free boundary. So that's what I'm talking about next. So the formulation we use, and there are other formulations, but this is a nice one, is the Zakharov-Craig-Sullivan formulation. This is what I wrote down before. I'm just repeating. That's Euler's equation and the boundary conditions. And here in red is the Zakharov-Craig-Sullivan formulation, where G is the Dirichlet-Neumann operator. So eta is the function defining the free surface, and psi is just the restriction of the velocity potential to the surface. And then it has this form. This you can look up in Craig-Sullivan paper, for example. The Dirichlet-Neumann operator simply takes you from Dirichlet conditions to Neumann conditions. That's basically, this is more or less the normal derivative of this function, of the function theta, which is this one. Okay, so we're going to be working in this context in these equations in red. G is gravity, P is the atmospheric pressure, constants, C is a constant, which is the speed of propagation. All right, so first, there's the Nekrasov-Levi-Civita theorem, which says that there's a curve of, locally, there's a curve of smooth traveling waves. And I'm just talking about the small, this is local bifurcation. You could think of this as local bifurcation. These are smooth functions and they're exact solutions. They're exactly traveling, they're exactly periodic, and they have an even odd character here. And that's a unique curve, given the two constants in the beginning. And in fact, many years before, like 70 years before that, Stokes had, even though he didn't have a rigorous proof, he said he wrote the expansions down for small epsilon. Everything is small. That is, the amplitude of the waves are small here. And he wrote this down as correct, even though, yeah, it goes way back to most of 2 centuries. Okay, so we have the Stokes wave. We're going to be perturbing from them. So we're going to perturb, we're going to linearize. We're not doing the nonlinear instability in this talk. So we linearize. So I'm going to use star. That's the speed. It's just a constant. And these two functions, I'm going to use star. Every time I have a star, it means the Stokes wave, something depending entirely on the Stokes wave and not the perturbation. So we're going to linearize. One thing is a little tricky, is linearizing the Dirichlet operator of eta acting on psi. And so you have the shape derivative formula of Lun. And also Alignac introduced something called the good unknown, which is this combination of the surface and the potential. This particular combination where B star, you see, is this combination, is this thing. You see, only B star and B star only depend on the Stokes wave. That's why I put a star on them. And so now you get this. So you get this equation in red. They act on functions of certain period. And you notice that you can think of this as, these are linear equations in V1 and V2 with coefficients that are variable. All the things with star, like this and this, they're variable coefficients that depend on the Stokes wave that you started with. Okay, so we're going to be working with this system in red. And then we do, now that system in red, that's for a free surface, but now we want to fix the free surface. We do that by a conformal mapping, which is pretty standard, although, okay, we have to make it fit our analysis. But so I won't go into the details. We're going to flatten the free surface by a conformal mapping because the velocity potential is a harmonic function, so we can do that. And after you do that, the Dirichlet-Neumann operator becomes this simple Dirichlet-Neumann operator here, which is just the function which in Fourier multiplier is just absolute value of k. And then it transforms into a system that looks like this. It's very similar to the other one, except that now we have a flat surface. We map the free surface into a fixed flat surface. And if you follow the Stokes formulas, the formulas of Stokes himself, and you figure out what P star and M star are in this equation, then it turns out they have these expansions. You can go further on in the expansions and find the coefficient here, and then you have higher order terms and so on. So now we're going to be talking about this system. Now we have that system. 8 and 9. Now we're going to do a little perturbation of the wave number. So that means we look at time-dependent solutions, which are exponentials, e to the lambda t, lambda is complex, and then e to the I mu x, where mu is small and real. So instead of w, which were the previous unknowns, we're going to transform to u, which are the new unknowns, u1 and u2. J goes 1 and 2. The Floquet parameter, mu is called the Floquet parameter. And it's quite convenient to take it as a rational number. Because then if you take it as a rational number, then, and if u has period exactly 2 pi, then w has period exactly L, which is the denominator, times 2 pi. So it's periodic. So if you didn't have a rational number, it wouldn't be periodic, and you could use the block transform, but this avoids using the block transform. So, so it's a convenient way to do it. Okay, so we're gonna just assume that, but that mu is a rational number only occurs on this particular slide, nowhere else. Anyway, when you do that, the previous equations, say I put for d by dt, I put e to the lambda t. So this becomes lambda, and this becomes lambda, and then you have an eigenvalue problem. So you get this eigenvalue problem, exactly this eigenvalue problem with the same coefficients as on the previous slide. But the mu, which is the Floquet parameter here, now appears next to the derivative, like that. Okay, I notice it's I mu x where mu is real. Okay, so this operator is a nice operator, acts on period, functions of period 2 pi. And what we want to prove is written here in blue. It means what we want to prove is that this guy, this operator in red, has an eigenvalue with positive real part. That's the whole thing reduces to that. Okay. One thing that's a little bit annoying, a little complicated, is that this is a pseudo differential operator. The others, everything else is a differential operator. Now, here I'm repeating the theorem. Epsilon parameterizes the Stokes wave. We're taking a Stokes wave which is near the trivial wave but not equal to it, and the Floquet parameter. And so that, I'm just repeating basically the same thing we said before, slightly more precise. We're going to show that there is an eigenvalue with positive real part, and here's the positive real part, and these are error terms. So this dominates these guys. Now, to find such an eigenvalue requires quite a bit of work. So we're going to, okay, we're going to look, yeah, let me go back. So we have the epsilon, yeah, here it is. The epsilon appears in these things with stars. They depend on the Stokes wave we've chosen, and mu just appears explicitly here. Notice it's almost linear. This is linear in mu. This is linear in mu. This is almost linear, not quite linear in mu. And this is linear in mu. Okay. Okay, so let's see. Okay, so when I take epsilon equals 0, then those coefficients, the variable coefficients become constants. And when epsilon is 0, it's just exactly this. And this is really simple to understand its spectrum because there are no variable coefficients. So you just Fourier transform in X. And remember, it's periodic. So I'm really talking about Fourier series here. So you write it as e to the I kx sum, e to the I kx sum over k. And then you can see exactly what the spectrum of this operator is, it's exactly these, where k is an integer and mu is always a small number, much less than an integer. And I just denote it this way. And okay, so if you take the special case when not only is epsilon 0, but also mu is 0, so that really simplifies this a lot, then you have 0 is an eigenvalue. You take k equals 0, and now mu is 0, and so lambda equals 0 is an eigenvalue, but it's an eigenvalue with multiplicity 4. This is well known, very well known. Now, when mu is not 0, what happens is that the 4 things in the null space or generalized null space split and go up the imaginary axis, and the 2 in the positive imaginary axis and 2 in the negative imaginary axis, and they're simple eigenvalues. Okay, but that's not good. We have to take epsilon non-zero. So that's the next thing. So now first we consider epsilon. Okay. First we consider epsilon non-zero and mu equals 0. But it turns out that when mu is 0, we still have a multiplicity 4 spectrum. There's still a 4-dimensional generalized null space, and it's explicit. It's more or less explicit. Well, I'm writing it here using some of the previous notation that I kind of sloughed over before. All these things with zeta has to do with the conformal mapping that I used to flatten the free surface. So, but there are, here I've written them. So this is written, this is a vector, so transform, that's 0, 1, and this is a vector, first component, second component, and so on. These guys are eigenvectors when mu is 0. And these guys are almost eigenvectors. They're generalized, as you see. So you have U1, U2, U3, U4, they're linearly independent. And U3 and U4, you see, satisfy, see U3, L of U3 isn't 0, but it's equal to a multiple of U2. And similarly for this one. So you have a 4-dimensional generalized eigenspace. And then it turns out very useful. You know, I didn't say so much about the detailed thing here, but if you normalize this guy, that's why I put a tilde here, you normalize it a little bit this way, then you can make it so that the same idea, but U2 now has mean 0. And as I mentioned, U1 is just the vector 0, 1. But U2, U3, U4, here they are in their expansion. So we can compute the expansions, again, going back to Stokes, 1850. And here's the beginning of the expansions of all of them. So you've got a 4-dimensional generalized null space kernel. Now we're going to take the epsilon, we're going to fix the epsilon and perturb in the mu. So remember, before we had epsilon equals 0 and we perturbed in mu, that just gave us imaginary eigenvalues. But now we have epsilon non-zero and we perturb in mu. And to do that, we use Lyapunov-Schmidt. So we, Bridges and Mielke also use Lyapunov-Schmidt. In that respect, it's the same idea as they did. So Lyapunov-Schmidt means you look at the kernel, the generalized kernel, which is 4-dimensional, and then you have an infinite dimensional part. So let U, script U, is the generalized kernel, 4-dimensional of L. Oh, this is generalized kernel when mu is 0. And pi is the orthogonal projection onto the infinite dimensional part. And then we write down these two equations, which is standard and dynamical systems stuff. So we have this, so one of these, so this equation is infinite dimensional and this equation is 4-dimensional. And so we look for a solution which is a linear combination of these guys where mu is 0 plus the infinite dimensional part. Here's the infinite dimensional part. Okay. And then the W is such a combination, and then W satisfies this equation. So the idea with Lyapunov-Schmidt is you solve for the infinite dimensional part, throw it into the other part, and then you get, in this case, a 4-dimensional system of equations to solve. So here I'm just repeating what our linear operator, this is the linear operator we're working with exclusively. And we can decompose, as I mentioned, it's linear in the mu, except for a slight absolute value here. And in fact, with infinite depth, it's exactly linear in mu, with a part where mu is 0 and a part first order mu. There's no mu squared term. With finite depth, you get also higher powers of mu in this expansion because this is a more complicated function with finite depth. Okay, so this guy has order 0. There's no other mu. Mu only appears here when we split. And now we want to, so we do what I said. We take this equation here for the W, and we solve for it, but I'm splitting this into the part, expand this in powers of mu, but there's only, it's linear in mu, basically. So here, and then I put all the things with W on the left side and all the things without W on the right side. And okay, and so now we can invert this guy. And then this, notice this has mu in it and a lambda. So mu is going to be small and lambda will also be small. It's a complex number. These are small, so we invert that, and then we're going to use expand with this thing being small numbers. Okay, so first we have to invert this operator. Okay. And okay, so this just says it's in that this operator has kernel which is the script u, the 4-dimensional guy, and the range is the infinite dimensional guy. And so we can take the inverse of it restricted to the infinite dimensional piece. I go from here back to here. Okay, okay. So that inverse, I'm giving a new name, call it Xi. So when you do that and you use the fact that those other terms, you have a mu and a lambda, which are small, so we have a Neumann series. So we can write the W's. This is a rather complicated thing. It's really a very complicated thing here, but it, in principle, we have a formula for W. Not very useful to use directly. Okay, so I call W's, following Benjamin's terminology, I call the W, it's W1, W2. No, sorry, W1 up to W4, I call them sideband functions. Okay, they turn out to be not so insignificant. Okay, so so here we have our basic Lyapunov-Schmidt expansion with unknown complex constants here, and we stick it into the previous formula, and we get four. This is the 4 equations. J goes from 1 to 4 here. And we're looking for a solution for the alphas, those four coefficients, which are complex numbers. And so it's just a 4x4 linear system. And so you just set the determinant equals 0 to find a non-trivial solution. We want a non-trivial solution, and then we want to show that lambda has a positive real part. So it looks like this. Unfortunately, oh yeah. So what I've written the part involving the sideband functions, I call that B, and the part that doesn't involve, I call A. This is lambda, essentially the identity here. So this is almost the identity matrix. So it's just this. This is the A part, and this is the B part. Okay, but we have just a 4x4 determinant here. Okay, so first it's a little complicated. I mean, the detail, a lot of calculation to do here, but we will compute this by expanding according to Stokes in small powers of epsilon. Yeah, small powers of epsilon and mu. Okay, so, oh yeah, here a summary is we want to find a number mu, an epsilon and a mu, such epsilon's fixed for the time being, epsilon and mu such that there is a solution of this fourth degree polynomial equation for lambda with a positive real part. Okay, so we do some pretty long calculations because you have 4x4 determinant, that's 16 things, entries. And okay, so we compute explicitly using all the from now on, it's all expansions in powers of epsilon or mu, everything. So we compute those things. And the part that does not involve the sideband function, we end up, I mean, there's 16 calculations, but maybe about half of them are pretty trivial and so on. Whatever, it's explicit, we explicitly do that. And so if we ignore the sideband functions, then we take this determinant of this 4x4 matrix, and it's exactly this. You just take that determinant. So you have to look at all the different things that make up the determinant. Okay. And I organize them in this way. So I have high powers of epsilon here, high powers of mu and lambda here, very high powers. These have not so high powers. And this is a term, this is also not so high power. Notice it's cubic. Okay, so that's what it is. And notice that when you set this equal to 0 and we ignore all the error terms, you might say all these terms in black, you just look at this, then the root for lambda is 1/2 I mu, which is purely imaginary. It's not what we're looking for. So we look at the other part, which normally in Lyapunov-Schmidt is not important, but here it's really important. So we do the calculation of all the terms involving the sideband functions, excluding the part that doesn't involve the sideband functions. And then a calculation similar to the previous one gives you this polynomial for the determinant. So here's something, okay, so here you got this number in here. I put it in red because that's the crucial term. And here we have, you know, a quadratic in lambda and a quadratic in lambda, and then it's a fourth degree polynomial, a quartic. Okay, and now when I put together the two previous things, the two previous calculations, it comes to this. So here you have the part coming from the A part, and here you have the important term, which I've written in red, which is this term coming from the sideband functions. Here's the epsilon squared. So this has no epsilons in it, so it's the leading term. but it does have mu's. All right. And then you have these other terms which have this combination 1/2 I mu minus lambda in them. And then you have even smaller error terms, epsilon cubed or mu fourth. And these big O of epsilon cubed that I'm writing here, they only depend on epsilon. They do not depend on mu or anything else. Okay, so that's P. And notice in P, see, good. Notice in P that mu and lambda, if we think of the pair mu lambda, it's cubic here. And this is cubic. And this is cubic. There's a mu here and the 2 mu and lambdas here. And this is cubic. And this is cubic. I said somewhere that the previous slide that this thing is cubic. And this is not cubic. But all the almost everything except this last guy are cubic. So we can scale. Let's do a little scaling. Let's do this scaling. So I take lambda divided by mu and I call that gamma. And now, okay, and now I use a tilde for that. I pull mu cubed out. And now we have just a polynomial in gamma. So now we have a polynomial in gamma. And we want to find, we want to find lambda. That means we want to find gamma. So now we're looking for gamma with a positive real part. Mu is real. So, okay, we want to, yeah, okay. Gamma is complex. And these guys, this is a constant. That's a constant, complex constant. Okay. And now we look, so now, okay, we're almost at the end of the proof. It's pretty explicit, as you see. So here the leading term is going to be gamma equals 1/2 I, which is not what we're looking for. Then we have this guy. So let's look at this combination and write down, take a new variable and just call mu. I'll call mu I divided by 2 plus kappa epsilon, just the scaling thing. And then you're going to, when you do that, you're going to get epsilon squared. By doing that, I get epsilon squared as a factor here, and here's a factor epsilon squared, and the epsilon squared factors here and here. Also, so if you just write this down from the above, you're going to get kappa squared from the first term that's in blue, minus 1/8, which is the term in red. Then you're going to get this other term, which is with R1, which is kappa, going to be kappa squared, epsilon squared. So I took the epsilon squared out. And the same with the next term. And then you're going to get this term, which is going to be of this form. It still has another epsilon in it. It has epsilon cubed, so there's another epsilon here, times something that's good. And then I've split off the very last term separately. I'll do that in a moment. So forget this term for a moment. And okay, you look at this thing, we want to look at the roots of this for kappa. So when epsilon equals 0, obviously the roots are 1 over the square root of 8 from here. And so we use the implicit function theorem, and they're going to be implicit function theorem to take care of these guys. And there's a curve of roots, kappa, there's a plus and a minus case of epsilon, like this. And so we have, yeah, so we have, for the part where I neglected the last error term, we have 2 roots, which they look like this, where kappa plus minus, when epsilon is 0, is just plus or minus 1 square over square root of 8. It's real. That's what we wanted. And now the only thing we have to do is take care of that last error term. So the last error term, which I denoted this way, you do by another implicit function theorem. It's not a problem. And so at the end, we get this. This is the theorem I've stated This is the third time I'm stating the theorem. So I want to emphasize that. Okay, so we chose an epsilon naught on a previous slide, small enough so something happened. That was for the implicit function theorem. And so if epsilon is small enough, this is small. So epsilon is small enough and mu is small enough, is in the, oh, in some interval, there should be another parenthesis here, then the determinant has two simple roots, which are exactly of this form. And when you do the second implicit function theorem, then you just get, it looks of this form, where these g's are smooth. Yeah, there's one for plus and one for minus. Anyway, so that's the theorem again. So here's the 1/2 I mu, and here's the real part. And that's the proof. So I'd like to just comment a little bit about the proof. I thank you for your patience in listening to so many details. I spared you a lot of explicit calculations of expansions in epsilon. So we could have begun from a different formulation of the problem. We didn't have to start, I believe, from the Zakharov Craig Sullivan formulation, but that is a nice way to do it. And maybe using a different formulation, we could, some of the calculations could be done a little more simply, but we're pretty convinced that you can't do the main ideas of the proof seriously more simply, except in terms of the calculation, accepted calculations. And I want to emphasize that in this proof, epsilon is chosen first. That's how far you go. That's the amplitude parameter of the Stokes wave. And mu is chosen later. That's the floodgate parameter. And mu could be much smaller than the epsilon. You choose the epsilon first, and then you choose the mu. I think that's really quite a serious thing to do. And in fact, the same two parameters occurred in Bridges-Mielke, and they have the same situation as this. They choose the epsilon first, and then they choose the mu. So that's some general remarks. Anyway, thank you very much.
Getting a few